All right, good morning, class. Welcome to this lesson on momentum 2, more impulse and momentum theorem. Okay, so this is going to be more of the same as the last video. Okay, we will be able to describe how momentum and impulse are related using qualitative examples. So these are more examples of the same stuff. So I want to cover the formula one more time, go over a couple graphs, and then give you a couple examples here. So let's look at this formula one more time. F delta t equals m delta v. I want to remind you that the units for this are, I'll write down here, kilograms meters per second, and this is momentum, right? Or the change of momentum, and this is impulse momentum. The units for impulse are Newton seconds. You can see that from this right here. Force is Newton, time is seconds. I want you to know that these two are the same thing. These two are the same thing. If we broke this down right here, because this is already broken down, if we broke this down right here, we would have kilograms meters per second squared times seconds. Seconds cancel out. Kilograms meters per second equals kilograms meters per second. So you might see this unit here, you might see this unit here, but really they're the same thing, okay? We tend to use this for momentum and this for impulse, but the reality is, as you can see here, the change in momentum is impulse. So these two are very, very closely related, okay? And I have to warn you at this point, we have displacement, velocity, acceleration, force, work, power, and now momentum. And all of those things use meters, seconds, and kilograms. Okay, all of those use these basic units. So you have to be really careful, and you have to really know what you're talking about. Okay. Notice, I mean, even just looking at energy. Energy is 1/2 mv squared. How closely is this related to this, m delta v? We have m delta v here, and then we have 1/2 mv squared. These two are almost the same thing if we just look at what's in the equation. And you can for sure bet that when it comes to when it comes to AP test questions, one part, part D is going to be on momentum, part E is going to be on energy, and you have to be able to distinguish between those two and how to solve for each one. Okay, so just keeping that clear, okay? Those are the units. Also, I did go over this a little bit in the last video, but I wanted to be, once again, clear. Force, time. It is very, very common to measure objects and measure what force is applied for how long, and you might be able to guess from this that if we took the area of this, the area is going to be the area under the curve, which is going to be force times time. So the area under this is going to be the impulse. Okay, the area that is going to be the impulse, which equals the change in momentum. So based off this graph right here, I could calculate, say, the final speed. Okay, if we'll say the initial speed was 0, okay, 0 meters per second, I have F times t equals m v final minus v initial. This would be 0, and then all these this is from the graph from above. And then I would give you mass in the question. So you can see that we can take this graph to solve for a lot of other things. And this just goes back to what I've been saying originally. For example, I'm bringing it up again, we can have a velocity time graph, and the area under a velocity time graph is distance. We could have a force and distance graph, and the area under that is known as the work. So once again, area under a graph is known as the y-axis multiplied by the x-axis, y multiplied by x, y multiplied by x. If we know what y and x are, we know what we're solving for. And so it's very important that you pay attention to details and look at your units, okay? So whenever we solve for these things, if you plug your units in and cancel out what's inside these equations, you're going to be able to see very quickly what you're solving for. Okay, so this is an example of area under a graph. So that's that. Let's move on to a couple more examples and we'll be done with this. Common question, and it doesn't have to be this, but pot falls on guy's head. Pot falls on on guy's head. Question, does it hurt more? Does it hurt more if pot breaks or bounces up? If this pot fell on this guy's head and broke and just kind of dirt fell all over him, would that hurt more, or would it hurt more if it actually hit his head and then came back up? And the answer to this question, it would hurt more if it bounces. It would hurt more if it bounces, because this object has a velocity, right? It has an initial velocity, and we'll say it's 10 meters a second to make it easy. And when the pot breaks, the final velocity is 0. So Ft equals m delta v. Well, delta v is now m times 10. Okay, Ft. Would it hurt more? Well, what we're really solving for is force. So we divide by time, and so F would equal m times 10 over time. So this force is what the man's head would feel. Equal and opposite forces, whatever force the pot hits his head with, his head hits the pot with, right? So this is what we feel, okay? So our next question is if it bounces up. Well, let's take a look at that, okay? Well, if it bounces, let's say it bounces with 5 meters a second. So the initial velocity is 10, and the final velocity is 5, okay? Well, notice we now have an up and down situation here. So I'm going to call this plus 5 and negative 10. That's not very easy to read, okay? Plus 5 and negative 10. It's moving down. I'm going to call down negative. I'm going to call up positive. I'm going to call up positive. So it's moving down at negative 10, moving up at positive 5. So if we have F times T equals m delta V, F times T equals m 5 minus negative 10. So Ft equals m times 15 meters per second. And if we solve for force, we're going to get m times 15 meters a second over t. Whatever our t is going to be the same. Whatever our m is going to be the same. So notice here that 15, this value is 15. The force on his head is going to be larger. It's going to hurt more if it bounces. It requires a larger force. It requires a larger force. It requires a larger force to stop the pot and essentially push it back up. The pot has to stop and go back up, versus before it just had to stop. So there's going to be a greater impulse. There's going to be a larger force over the same period of time to make this change in momentum. Okay, so let's look at one more. This is also a very common question, and it has an obvious answer. Imagine standing on your desk at school and jumping off the desk. Imagine jumping off the desk with your knees locked. Imagine jumping off the desk with your knees locked versus knees bent. What would hurt more? What would hurt more? Well, this is pretty obvious. Okay? It would hurt more if your knees were locked. But why? Let's say when you jump off the desk, you are traveling you end up traveling at 5 meters a second, and then you stop, which you're at 0 meters a second, right? So we're jumping and we're going from 5 meters a second to 0 meters a second. We have the same mass, okay? M and delta V is going to be 0 minus 5. So we're going to have m times negative 5 meters a second. Our change in velocity, our momentum change, is going to be the same no matter what we do. In this situation, we apply a very, very large force over a short period of time to stop us because our knees are locked. If our knees are locked, we stop very, very quickly. So this is a very short period of time, large force. In this situation over here, we have the same thing, but now we have a larger period of time and a smaller force because we slow down. So there's a longer period of time with this one on the right versus this one on the left. So this is just another example of impulse and momentum. The impulse is the same for both. The change in momentum is the same for both. But the reality is, one has a larger force over a shorter period of time, one has a smaller force over a larger period of time. And this is why, and in any problem, most of the time we're going to calculate one of these two things here. What force is applied, or how long did it take? Or we might end up solving for mass or velocity. We can solve for anything in here. It doesn't matter which one we do. But it's very common to solve for either this or this. How long did it take to stop it, or how much force do we have to apply to stop it?